Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on graph theory, lecture number 24, in which I will give the concept of label graph and prove the Cayley's theorem. Now we will discuss about counting and label of trees. In 1857, Arthur Cayley discovered tree while he was trying to count the number of structural isomers of the saturated hydrocarbon. The molecular formula of saturated hydrocarbon is CkH2k plus 2. He used a connected graph to represent CkH2k plus 2 molecule corresponding to their chemical valencies. A carbon atom was represented by a vertex of degree 4 and hydrogen atom by a degree 1 pendant vertex. As the chemical valency of carbon atom is 4 and chemical valency of hydrogen atom is 1. So, carbon is represented as this degree 4. Here 4 edges are incident to carbon atom and hydrogen edge degree 1. One edge is incident to this vertex, H vertex. Now we count the number of vertices in CkH2k plus 2. Since in CkH2k plus 2 molecule has k number of C and 2k plus 2 number of H. Since each C represents a vertex and also each H represents another vertex. Therefore, number of vertices due to vertex C be k and number of vertices due to H is 2k plus 2. Therefore, total number of vertices equal to here k vertices C k plus here 2k plus 2 for H 2k plus 2, that is equal to 3k plus 2. Let this is n. Let this is number 1. Since each C is of degree 4, therefore total number of degree contributed by K number of C equal to 4K. This is number 2. Since each H is of degree 1, therefore total number of degrees contributed by 2K plus 2 number of H equal to 2K plus 2. Since 1H gives rise 1 degree, therefore total sum of degrees equal to 4K plus 2K plus 2. This is number 3, and this is equal to 6K plus 2, and this is equal to 3K plus 1. This is number 4. We know that one edge gives rise 2 degree. Therefore, total number of edges will be total sum of degrees by 2. Therefore, total number of edges equal to 2 multiplied by 3K plus 1, total sum of degree by 2. This is 3K plus 1. Here we have 3K plus 2 equal to n. Therefore 3K plus 1 will be equal to n minus 1. This is number 5. From 1 and 5 we get that the graph has n vertices and n minus 1 edges. Since in saturated hydrocarbon we see that the structure of saturated hydrocarbon is like this. And in saturated hydrocarbon we get no cycle or circuit. Therefore, the graph has n vertices, n minus 1 edge and no circuit. Therefore, the graph has n vertices, n minus 1 edges and no circuit, as the graph is connected. Therefore, the structure of saturated hydrocarbon represents a tree. Thus, the problem of counting structural isomers for a given hydrocarbon becomes the problem of a counting trees. With the help of 4 distinct vertices, or level vertices. 16 different trees of 4 leveled vertices may be possible in the following figure. We may see this. Here we have 4 distinct vertices A, B, C, D. Here in the first row, we see that the degree of vertex B be 3. In the second figure, degree of A is 3. In third figure, degree of C is 3. In fourth figure, degree of D is 3. These are 4 different graphs. In the second row, we see that here degree of B and C be 2. In the second figure, degree of A and D be 2. And in the third figure, degree of A and D be 2, but
A and B are connected here. Here A and B are not connected.
and C and D are not connected. In the next figure, we see that degree of B and C be 2. In this way, in the second row, we get 4 different graphs with 4 vertices. In the third row, we see that
A and C are connected. Here A and C are not connected. Here C and D are connected, but here C and D are not connected. Here C and D are connected.
in this figure, A and B are connected. Here A and B are not connected. So, in the third row, we get 4 different graphs. In fourth row, we see that here A and B are of degree 2. Here A and B are degree 1. Here degree of A is 2, but degree of B is 1. Here degree of B is 1, here degree of A is 1. So this is different from this. And here in this figure, degree of B is 2 and degree of D is also 2. So we get 4 different graphs in this row. A graph which is assigned to a unique name or level. Here levels are A, B, C, D. Is called a leveled graph. The 4 graphs in the first row are counted as different trees, given that they are isomorphic. Only because the vertices are leveled. If there were no distinction made between A, B, C, D, these 4 would be counted as 1 here. If we have no A, B, C, D level, then 4 graphs will be the same. In each graph, we see that one vertex is of degree 3 and other vertices are of degree 1. If we do not speak about leveled vertices, that is unleveled, then only 2 graphs would be made for 16 graphs. Only we get 2 graphs for these 16 graphs. One graph will be this first vertex, second vertex, third vertex, fourth vertex. Here we may take this A, then B, then C, then D. Here also B, A, D, C. All are like this. All are these row and these row become like this. And first row is of the form the second structure. Now we state and prove Cayley's theorem. Statement: the number of labeled trees with n vertices n greater than equal to 2 is n to the power n minus 2. Before proving Cayley's theorem with n vertices of the tree, we take a particular case and we see that how the Cayley's theorem is proved. Let we have a labeled tree. Here vertices are labeled with number 1, 2, 3, 4, 5, 6, 7, 8, 9. Now we write 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, by some rule, we prepare a sequence. For this, we remove the smallest label pendant vertex with its edge, and we write the vertex which is adjacent to that smallest label pendant vertex. Here, smallest label pendant vertex B2, we delete this, and here also we cancel this, and here we have 1, we write this. Now, smallest label pendant vertex B4, we delete this and cancel this, and this is adjacent to vertex 1. Now, smallest label pendant vertex B1, we delete this, and here we also cancel this. The adjacent vertex B3, we write 3. Now, smallest label pendant vertex B3, we delete this, and we write the adjacent vertex 5. Here we cancel 3, here we write 5. Now, smallest label pendant vertex B6, we delete this, and we write the vertex adjacent to 5. Now, smallest label pendant vertex B7, we delete this, and we cancel here also, and we write the adjacent vertex 5. Now, here smallest label pendant vertex B5, we delete this, and we cancel this here, and we write the adjacent vertex 8, and we complete our sequence. Now, with the help of this sequence and also this sequence, means label of vertices, we again construct a tree, and this tree will be the same as before, which already deleted. Now we take the first number which is not present in this sequence. Here first number is 2, and we take here first label vertex. Here 2, Here first level vertex is 1. We cancel this 2 and this 1. Now we see that number present in this sequence is not present in the second sequence. Here 4 be the number which is not present in the second sequence. We take 4 and then we take first number 1. Here we cancel 4, here 1. Here we write 4. Now we take next number in this sequence which is not present in the second sequence. Here 1. 1 is not present in the second sequence. We take 1 and then first number is 3. 1, we connect 1 and 3. We cancel 1 and 3. Now we select any number in this sequence which is not present in the second sequence. Here 3. 3 is not present in the second sequence. Then we connect 3 and first number 5. 3 and 5. We cancel 3 and this 5. Here we find the number which is not present in this sequence. Here 6 is not present in this sequence. So we take 6 and here first number 5. We connect 6 and 5. 6 and 5. We cancel 6 here, we cancel 5 here. Here we see a number in this sequence which is not present in this sequence. Here 7 is not present in this sequence. We take 7 and connect with 5. First number here 5. 5 with 7. We cancel 7 here, we cancel 5 here. Now we find a number in this sequence, first sequence, which is not present in the second sequence, that is 5. And 5 is connected to first number 8. 5 is connected to first number 8. 5 is cancelled, 8 is cancelled. Our complete next is 8, 9. We connect 8 with 9. Then we find that in this process we get the same tree which was deleted by the first process. We will follow this process for proving the Cayley's theorem. Here we see that in the second sequence we get 1, 2, 3, 4, 5, 6, 7 numbers. In the first sequence it was 9 numbers. So second sequence contains 2 less numbers. And here also we see that any number may be repeated here. Here 1, 1, here 5, 5, 5. So if we have 9 numbers and we may take any of 1, 2, 3, 4, 5, 6, 7, 8, 9 in the first place. In the second place we may also take 1, 2, 3, 4, 5, 6, 7, 8, 9, any number. And in this way we have to fill 7 places in which a number may be repeated. And that process will be 9 to the power 9 minus 2. Means 9 to the power 7. Now we prove the Cayley's theorem. Let the number of vertices of a labeled tree be n. Let vertices be labeled by number 1, 2, 3, n respectively. Let us remove pendant vertex having the smallest label with the edge incident on it. Let this pendant vertex be A1 and let B1 be the vertex adjacent to A1. And let us remove the edge A1, B1. Among the remaining n minus 1 vertices, let A2 be the another pendant vertex with the smallest level, and let B2 be the vertex adjacent to A1. Now we remove the edge A2, B2. This process is repeated on remaining n minus 2 number of vertices, and then n minus 3 number of vertices, and so on. The process is terminated after n minus 2 number of steps, when only 2 vertices are left. In this process we get a sequence. Here we take B1, then B2, comma dot 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 B n minus 2. This is number 1 sequence. In the converse way, with the help of sequence in 1, the same tree may be constructed, as we have n labeled vertices, and we make another sequence 1, 2, 3, comma dot 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 n. This is number 2 sequence. Now let us determine first member in sequence 2, which does not appear in the sequence 1, is clearly vertex number A1. Here we have removed A1 and B1. Now edge A1 and B1 is constructed. Here we have removed the edge A1, B1. Now we construct the edge A1, B1 in the converse way. Now we remove this B1 along with A1 from this sequence. In the remaining sequence of 2, let us find the first member which does not appear in the sequence 1, and let us find the first member that does not appear in the remaining sequence of 1. This would be A2. Here we have seen A2, and the edge A2, B2 is constructed. This construction is continued till the sequence 1 has no element left. Finally, last 2 vertices are joined. As the sequence 1 is unique, this sequence is unique for a particular level tree. Since number of possible sequence denote number of possible level trees, it is obvious that any element of sequence 2 can be repeated by some or n minus 2 times to form the sequence like 1. Number of possible sequence will be equal to n multiply by n multiply by n multiply by dot 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 n minus 2 times, because the first place of sequence 1 can be filled by one of n numbers. The second place also may be filled by one of these n numbers. In the similar way, n minus 2th place may be filled by 1 or 2 or 3 or n number. Therefore, to form the different sequence, we get n multiply by n multiply by n multiply by n dot 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 n minus 2 times. That means equal to n to the power n minus 2. Since number of possible sequence equal to number of label trees, this particular sequence 1 denote a particular label tree. Therefore, if this sequence is changed, then label tree will be changed. And this number of label trees will be equal to n to the power n minus 2. Hence, there will be n to the power n minus 2 possible label trees with the help of n vertices. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.